Welcome students. This is my first lecture of your course. Myself Dr. Soumen Samanta, Assistant Professor of Department of Applied Science and Humanities, India Institute of Technology. Today I will give you basic introduction concept of matrix and rank, and lastly how to find the rank from a matrix using elementary operation here we will discuss. So this is my subject matter of today's lecture. First of all, what is matrix? Types of matrix with examples, algebraic operations on matrix, transpose of matrix and its transpose, and its properties, symmetric and skew-symmetric matrix, inverse of a matrix, adjoint of a matrix and its properties, trace, orthogonal matrix, rank, and elementary operations, row reduced, row echelon form, find rank and inverse of a matrix using elementary operation, and lastly I will provide you some questions for practice. Okay. Before we start, first we have to know what is matrix. So today's lecture we have two parts. Part A, the basic we discuss the basic concept of matrix, which we started in 12th class. So, and next part we discuss the rank of matrix and how to find the rank using elementary operation. So, first we have to know what is matrix. A matrix is a m cross n rectangular array of mn elements surrounded by a square bracket. Square means either it is first bracket or second third bracket, where the elements comes from these elements comes from the field either it is real number or complex number. So today's lecture we only consider the elements are real number. Okay. The lines of numbers going from left to right. These are the lines from the numbers left to right. These are called the rows, and the lines from the of numbers from top to bottom like this. So this is the column. This is another column. These are called column. Here m denotes the rank, m denotes the number of rows, and n denotes the number of columns. Most cases, on many times, we denote a matrix with capital letters A, B, or C, etc. Then, if the number of rows in a matrix is equals to 1, it is called row matrix. If the number of column in a matrix it is 1, it is called column matrix. This is the example. Here A is, here you see that number of rows in this matrix it is 1, and so it is called row matrix, and number of column in this matrix is 1, it is called, this is the example of column matrix. Next, square matrix. Square matrix means any matrix whose number of rows and number of columns are equal, it is called square matrix. Here it is an example of 3 cross 3 matrix, square matrix. Here number of rows is 3, number of columns are also 3. It is called square matrix. Zero matrix, if all the entries in the matrix are zeros, it is called zero matrix. This is the example 2 cross 3 zero matrix. Anyway, next, diagonal matrix. A square matrix is said to be diagonal if all the entries are 0 except the principal diagonal. This is called principal diagonal. Except this principal diagonal, all the entries are 0, then it is called diagonal matrix. This is the example. Identity matrix. A diagonal matrix is said to be identity matrix if all the entries, all the elements of the principal diagonal are 1. It is called identity matrix. This is the example of 3 cross 3 identity matrix. In general, you can say that this is IN. In generally we denote as identity matrix is I, and N stands for the order of the matrix. Next, upper triangular matrix. A diagonal matrix is said to be upper triangular if all the entries below the principal diagonal, are 0. This is called upper triangular matrix. So you don't look above principal or entries above principal diagonal. It may be 0 or may not be 0, but you should only think about the entries below the principal diagonal. If all the entries below the principal diagonal are 0, then it is called upper triangular matrix. Similarly, lower triangular matrix, if all the entries below the principal diagonal are all the entries above the principal diagonal are 0, it is called lower triangular matrix. And triangular matrix, if it is either upper triangular or lower triangular, this is called triangular matrix. Next, we give some algebraic operation on matrix. Actually, all these concepts we are already studied in class 12. So we recapitulate these concepts once again before we start the concept of rank. What is the multiplication of a scalar? Any matrix A, we generally denote as this Aij. So if a matrix A multiplied by a constant C, that means what is C into A? That is C into Aij. That means all the entries multiplied by C. Similarly, at this addition of two matrices, first you have any two matrices of any order, you cannot be added. So, what is the criteria for addition of two matrices? That is, they should have the same order. If A and B two matrices having the same order, then addition is defined. And how? And component-wise addition. Component-wise addition means, suppose a matrix 2, 3, 1, minus 1 plus 0, 1, 2, 3. Then what is the resultant matrix of these two? Component wise addition. This is the first component of this matrix, this is the first component of this matrix. So 2 plus 0 is 0, 3 plus 1 is 4, 1 plus 2, 3, minus 1 plus 3, 2. So this is the resultant matrix of this addition. Similarly, you can know C into A plus B, that is equals to CA plus CB, C plus DA, that is equals to CA plus DA. Matrix addition, this is most important. Matrix addition is commutative, and matrix addition is follow the associative property. This is the property of commutativeness, and this is the property of associativeness. And multiplication of two matrices, any two matrices, not be multiplication is not always possible. What is the condition? If a matrix, suppose A here, A is a matrix of order n cross n, and B is another matrix of order p cross q, then what is the criteria to define AB, product AB? It is possible only when if these two are equal. If n equals to p, that means number of column is equals of A equals to number of rows of B. If this equals, then AB is defined, and BA is defined if similarly Q equals to M. And what is the product of these two matrices remaining? That is AB matrix of order n cross q, and BA matrix of order q cross n. So, this is the method how to find the product AB, that is called Cij. Cij you get Aij into Bkj, where I run from 1 to n and j run from 1 to p and k run from 1 to n. Matrix multiplication is not commutative. Here you see addition of two matrices follows the commutative property, but in this case it is not always true. AB not equals to BA. And matrix multiplication is follow the distributive property with respect to matrix addition. This is the distributive property, and you studied in class 12. And if you see any example, matrix multiplication is not complete, take any two example of square matrix. Suppose 2 plus 2, you can check this is not equal. Now, transpose of a matrix. Transpose of a matrix is defined by this. AT equals to, suppose A is any matrix, suppose A is any matrix, A equals to Aij here, M cross N, then A transpose is defined, denoted by this and defined by Aji. Just row replaced by column and column replaced by row. That is N cross M. Here, this is an example. Suppose here A is 2 cross 3 matrix. And what is A transpose? Transpose of A just row here in column and elements of the row, second row in the second column. And there are some basic properties of transpose, that is AT. Again, you can take the transpose, you get the original matrix A, then A plus B transpose equals to A transpose plus B transpose, C A transpose equals to C times A transpose, AB whole transpose equals to B transpose A transpose. And all the proofs of all these concepts are elementary and you can see, you can prove easily. Next, symmetric and skew symmetric matrix. A square matrix A is said to be symmetric matrix if A transpose equals to A, and already we know what is A transpose, that is the transpose, A transpose equals to A, and skew symmetric if A transpose is equals to minus A. And this is the example. Here you can check A transpose equals to A. Look into this matrix. This is A. What is A transpose for this first? What is A transpose? This is equals to 2, 1, 5 first row, it becomes first column, then 1, 0, 4, 1, 0, 4, next 5, 4, minus 4, and it becomes the original matrix A. So that is why it is symmetric matrix. Similarly, if you see that after B transpose, now you calculate what is B transpose. B transpose means 0, minus 1, 7, 1, 0, 2, minus 7, minus 2, 0. Here it is not in the, not equals to B. So if you take common minus 1 from whole matrix, you get 1, 0, 1, 7, 0, minus 1, 7, 1, 0, 2, minus 7, minus 2, 0. Now it becomes B. So B transpose equals to minus B. That's why B is skew symmetric matrix. Also we have some properties of this symmetric and skew symmetric, that is A and B two symmetric matrix of same order, then A plus B always symmetric and AB is symmetric only this. If it satisfies AB equals to BA, then AB is symmetric, otherwise not. If A is any matrix, then A transpose and A transpose A are always symmetric. The diagonal elements of a skew symmetric matrix are all 0. This is a property, and you know it is simple. Just diagonal elements of a skew symmetric. What is skew symmetric matrix? That is A transpose equals to minus A. And what are the diagonal elements of this? Diagonal elements means AII, whose row and columns are equal. That means AII equals to minus AII. This implies twice AII equals to 0. 2 cannot be 0 provided characteristic of field not equals to 2. So therefore AII equals to 0. That means diagonal elements. AII means diagonal elements of the skew symmetric matrix as always 0. AB any square matrix, then A plus AT and are symmetric and A minus AT is a skew symmetric matrix. And lastly, every square matrix can be expressed uniquely as a sum of symmetric and skew symmetric matrix. Next, the concept is singular and non-singular matrix. And what is the definition of singular matrix? A square matrix is said to be singular if you calculate the determinant of that matrix, and if you get this is equals to 0, it is called singular matrix. And non-singular matrix if the determinant is non-zero. And we assume that everyone know how to find the determinant. So this is the example. If you take the determinant of this A, you get 0 here, and if you take this determinant of B, should be non-zero. You can check it. And what is the invertible matrix? An n-cross-n matrix A is said to be invertible if there exists a non-singular matrix B such that AB equals to BA equals to IA. Then B is said to be inverse of A and denoted by B equals to A inverse. So A, given a matrix A is said to be invertible if you find another matrix B such that the product AB and product BA is equals to identity matrix of that order. Then B is said to be the inverse of A, and we write it in this way. And there are basic properties. First find A inverse, then take another inverse. So you get the original matrix. AB whole inverse equals to B inverse A inverse, and A transpose whole inverse equals to A inverse, then transpose. Next, adjoint of a matrix. Let A be a n square matrix and capital Aij. Here look into this. A is a square matrix Aij, and capital Aij be the cofactor of corresponding Aij in data. So what is cofactor? Cofactor means minus 1 whole to the power I plus j into mij. And what is mij? That is called minor. So next, here you see the definition of minor. But how to find minor? Minor means, suppose mij, that means ith row and jth column, if you delete it from the given matrix, then the resultant matrix, if you take the determinant of the resultant matrix, you get mij. That is called minor without sign. And minor with sign means minus 1 whole to the power I plus j, that is called cofactor. Am I clear? So this is the cofactor of Aij element. So how to define adjoint A? Adjoint A is nothing but adjoint A. So first find cofactor of this, then after finding cofactor of all these Aij, then take the transpose. So that's why we write. Then the adjoint of A is denoted by adjoint A and is defined by adjoint A is equals to capital Aij whole transpose. So first you have to find capital Aij. How to find? Then first find minor, then with sign, it is called cofactor. And these are the properties. Adjoint of A transpose equals to adjoint A whole transpose. Adjoint of CA equals to C to the power n minus 1. Adjoint A, where n is the order of the matrix. Adjoint of adjoint A equals to data whole to the power n minus 2 A. And A into adjoint A equals to adjoint A into A equals to data into I. Next, trace of A. Given a matrix A, trace of A is defined as the sum of the all diagonal entries. That is the trace. So here the two examples we get A and B. So trace of A equals to 2 plus 0 plus 3, that is 5. Trace of B means 2 plus 0 minus 2, that is 0. So trace of A is equals to the sum of the all diagonal elements. Here are the basic properties of trace. Trace of C into A, that is C times trace A. Trace of A plus B equals to trace A plus trace B. Trace of AT equals to trace A. Trace of AB equals to trace of BA. provided AB and BA are defined. Orthogonal matrix. A real matrix n cross n is said to be orthogonal if AT, product of A and the transpose of A equals to IN. And this is the example. You can check and verify that this matrix is orthogonal. That means this is the given A, and what is A transpose? Thus, so first find A transpose, that is equals to cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. So this is A transpose. Next, just multiply A into A transpose. If you give the value of A transpose equals to IN, then you say this matrix is orthogonal. And this is the whole property of orthogonal matrix. First one, if A is orthogonal, the determinant of this orthogonal matrix should be always plus minus 1. If A is orthogonal, then A transpose equals to A inverse. If A and B two orthogonal matrix, then det of A plus det of B equals to 0. Then A plus B is singular. If A and B are orthogonal matrices of same order, AB and A inverse both are orthogonal. Up to this, all of you know all these concepts. Up to this, everyone studied in all these concepts in the higher secondary syllabus. So these are the basic preliminaries of my today's lectures. Now we are going to discuss the new concept in this course, in this topic, that is rank of a matrix. Now first, what is rank of a matrix? Rank of a matrix, any matrix, rank of a matrix is defined as highest order of non-vanishing minor. Highest order, there are three terms. Highest order, and non-vanishing minor. First, clear about the definition. Given any matrix of any order, you have to find the rank, and definition says that this is the highest order of non-vanishing minor. That means given any matrix, suppose here if you see the example, the B matrix of order 3 cross 4. Clear? This is the 3 cross 4 matrix, any order. So highest order of non-vanishing minor, that means you have to find first minor of highest order. So what the minor of this matrix of highest order? That is 3. Because 3 cross 4, when you find the minor, that means minor means just 3 cross 3 minor means 3 cross 3 determinant. 3 cross 3 determinant means here number of rows is 3, number of columns are 4, that is 3 cross 3. Here 3 cross 3 minor like this: 3 minus 1 1 0 4 2 minus 3 1 minus 1. This is a 3 order minor. So you can construct another 1 2 3, another 2 types 3 order minor. That is like this: 3 0 minus 3 minus 1 4 1 2 3 minus 2. This is another 3 order minor. Again minus 1 1 2 4 2 3 1 minus 1 minus 2. This is another 3 order minor. Similarly 3 0 minus 3 1 2 minus 1 2 3 minus 2. This is again a 3 order minor. So you have to find all these 3 order minor. And if you get these minor are non-vanishing, that means determinant is non-zero. If you get one of these three order minor is non-zero, you say that the rank of the matrix is 3. Clear? Once again, for this matrix, suppose this is a 3 cross 3 matrix, so highest order of this matrix is 3. That means minor of 3 order minor here is 1, only this. In this case, you see that this is a 3 cross 4 matrix, so you can choose which column you can take. Suppose this is the first 3, it is 1 minor here. Next, take this and this. This is another this. Sorry, this, another this. So many. If any one of these are non-zero, not check all these. Suppose you first find this is 3 order minor and take the determinant, find the determinant, and if you see this is non-zero, don't check other 3 order minor. So, but if this is becomes 0, this becomes also 0. So another, so all the 3 order minors are 0, then you go to the next highest, that means 2 order minor. Okay, here you can check, this is the 3 cross 3. Assume that these 3 cross 3 determinant are 0. That's why it is highest order, but it is vanishing minor. Next, go to the 2 order minor. What is 2 order minor? 2 cross 2 determinant. Here you can see that 2 cross 2 determinant, this, that is, suppose take any one, 2 0 1 0, and you can calculate the determinant of this becomes a 0. So 2 order minor, first you can take this one, this is becomes 0. So from this you cannot conclude the rank of is not 2. So take another, this is another 2 plus 2 minor, and here you can check the determinant is 4. So this case 1 0 minus 5 4, that is equals to 4, which is non-zero. That means rank of this matrix is 2, provided we assume that the highest order 3 cross 3 determinant is 0. Okay. So this is the basic properties of the rank of the matrix. So if you want to understand what is the definition of rank, once again I say, this is the defined as highest order non-vanishing minor. First calculate highest order minor, then find the determinant, and if the from highest order it is non-zero, that order is called the rank of the matrix. And this is the property for any matrix A, rank of A equals to rank of A transpose. For any square matrix A of order A, if A is singular, then if A is singular, that means, suppose here in this case we assume that A is singular, that means 3 cross 3 determinant is 0, that means A is singular. In that case, rank of A should be less than equals to less than order of this matrix. That's why rank of A is less than A. And if A is non-singular, then it is equal to A. If determinant of A is non-zero, then rank of is 3. Rank of a null matrix, that is 0 matrix, is 0. Rank of an identity matrix, that means identity matrix of order 3, suppose 1 0 0 0 1 0 0 0 1. Rank of this matrix is 3, because after calculate the determinant of this, it is 1, it is non-zero. So rank of any identity matrix is equals to n, that is the order of the matrix. Let A be any non-zero m cross n matrix, then rank of A is less than equals to minimum of m and n. But the difficult is that if your matrix is higher order, that means 5 cross 6, 6 cross 7, 10 cross 10, 50 cross 50, 100 cross 100, then using this definition, you cannot determine the rank of the matrix. This is the biggest problem. For that case, that's why we use elementary operation. There are 3 types of elementary operation. Using this elementary operation, and you can conclude rank of A is equals to number of non-zero row. We can see the later. So what are the elementary operation? In elementary operation of a given matrix, A is an operation of the following three types. Only you can apply three types elementary operation. One, you can interchange between two rows or two columns, and symbolically we write in this way: Rij or Crij. R stands for row, C stands for column. Rij means interchange ith row to jth row and jth row to ith. You can apply. Second, multiplication of a row or column by a non-zero scalar lambda. You can do this, and symbolically we write all the words. We can write only in this notation: Ri lambda. This means ith row multiplied by lambda, and we denote it Ri lambda. And third is most important: addition of a scalar multiple of one row or column to another row. Symbolically we write Rij. So Rij means, if you explicitly write Rij lambda, that means Ri plus lambda times Rj. This is most important elementary operation we apply in that. So Rij lambda means first multiplied jth row by lambda, then adding to ith row. Symbolically. Now this row reduced matrix, another two concept: row reduced matrix and row reduced echelon form. An m-cross-n matrix A is said to be row reduced if the first non-zero element in each non-zero row should be 1. Any m-cross-n matrix is said to be row reduced using the above three elementary operation. When you say it is row reduced, if the first non-zero element in each non-zero row. Here you see this example. First non-zero row is this is the first non-zero row, and first non-zero element is this, and this should be 1, and this one is called leading one. And second, in each column containing leading one of some row, the leading one is the only non-zero element. Here the second condition: in each column, suppose this is your column, first column containing leading one of some rows, that is fourth row, except one, all entries are 0. That is the second condition. So if your matrix, after applying the above three elementary operation, you get this type of matrix, it is called row reduced matrix. Check go to first row, first non-zero element should be 1, and this one containing this column, all entries are 0. Next, go to the second row, first non-zero element is this one is called leading one, and below leading one and above leading one all are 0. And third row, all are 0 elements, that is called 0 row. So we do not check here anything. And the last row, first non-zero element is this is called this one is called leading one, and above all entries are 0. So this matrix is called row reduced matrix. And check this matrix. First this is here is 1, this one is leading one. No, this one is not leading one, because first non-zero element, go to the first row, first non-zero element is this one is called leading one. Next, go to the second row, no, there are all entries are 0, so it is 0 row. Next, go to the third row, first non-zero element is 1, so this one is called leading one, and below leading one, above leading one, all entries are 0, and go to the last row, this is 1, and above all it is 0. So this matrix is row reduced matrix. Next, row reduced echelon form. Echelon. That means this matrix is row reduced, and extra condition for echelon is that like this: In the previous example, here you say this is the leading one, but this one is in second column. Here is also a leading one is in the first column. So you can interchange this to this so that they take this form. This is the condition. An M cross N matrix A is said to be row reduced echelon matrix if A is row reduced. Previous one, there is an integer R such that the first R rows of A are non-zero rows and remaining are zero rows. So all the zero rows should be in the last. In this example, there are zero rows in the middle, but it is row reduced. When row reduced echelon form, these zero rows should be in the last. These are all row reduced echelon form. So this is my today's lecture, and last we conclude with some two examples. How to find rank using elementary rule operation. That is the main application to find rank, and next class we will see how to solve the system of linear equation using matrix method and using elementary operation we discuss. So find rank using elementary operation. Here you see that it is 3 cross 3 matrix. So you can use this 3 cross 3 matrix find rank, use the definition. But we take a simple example so that we have used the elementary operation in this. So starting with this matrix, what is the technique? First technique. So every time you follow these 3 operations. This is the main. Every time you follow these 3. So first technique क्या है? Go to first non-zero row and first non-zero element. That element should be leading one using this 3 elementary process. But here we do not. Here first we use interchange between first and second row, because here we see that one is already present in the first place of second row. So if we interchange the first row and second row, then this one becomes leading one. Okay. Otherwise, you have to multiply it by first row by 1 by 2. So you can use that process also. But here we use first interchange between first and second row. Next, using this leading one, all the entries below this should be 0. Here below leading one it is 2. So how we get here 0? Using elementary operation, we use last one. Multiplied first row by -2. Right, in this way. Multiplied first row by -2, adding into the second row, we get 0 here. That is this. Accordingly, you change all these 3, because multiplied first row, that is -2 into 0 plus 0 is 0. -2 into -1, that is +2. Adding into the second row, that is -2, it becomes 0. Next, it should be 0 also, -5. So what is the operation we use? Use multiplied first row, because this is your leading one. Using only using this leading one, you should have all these below should be 0. Below and above. So multiplied 5 throughout the row 1, adding into the third row, we use this notation and getting this matrix. 1 0 -1 0 0 0, and 5 into 1 5 plus -5 0, 4 -5 plus 3 is -2, and so this leading one, job done. Next, go to the second row. Second row is 0 row. So no work done here, because we have to use non-zero row. Next, go to the third row. Third row first non-zero element is 4. So this 4 should be 1. What is the technique? देखो third row multiplied by 1 by 4, that is 0 1 minus half. So this is one leading one, this is another leading one, and no other leading one are there. So what is the rank? This is the find rank using elementary reversion. This is not this is row reduced. This is row reduced, but it is not row reduced echelon form. Using row reduced, after getting row reduced, what is the rank? Number of non-zero row after reducing the given matrix to row reduced or row reduced echelon form. Here we use only row reduced. Then rank of, here the rank of the given matrix is 2 because number of non-zero row is this one and this one 2. That is the rank of the matrix is 2. So you can, using this, you can find the rank. And last example, find A inverse using elementary row operation. What is the method? Given matrix A, you start with A, corresponding order here is 3. So 3, take the 3 plus 3 identity matrix and take as a whole, this is your matrix. Consider as a whole. So what is the technique? Given matrix your A and we have to find A inverse. Technique is taking identity of the order, taking identity matrix of the same order and take as a whole, this is a matrix. Now as the previous one, same technique, using 3 elementary operation, you have to reach I3, first place, plus I3 and then another matrix, name is B, then that is called the inverse of the corresponding A. Dekho, this is your matrix and this is a 3 cross 3 matrix, so we take 3 cross 3 identity matrix. What is the elementary operation we use? First non-zero row, first non-zero element should be leading one. So this is already one present here, so this one is leading one. Using this leading one, these 2 and 3 should be 0. So we use these 2 operations simultaneously. And you get previous slide, you see that how we apply in this way. Multiplied minus 2 in the first row, adding into this you get 0 here and correspondingly all the integer changes, and the second operation multiplied minus 3 adding into this you get this. So using these 2 operations we get this matrix. Next we go to the second row. So this leading one, job done, all the entries are 0. Next go to the second row. Here first non-zero element is 2, 2 should be 1 first. For that we use second row multiplied by half, we get this matrix. Second row, all the other entries are same. Next, after getting leading one, so what is the technique? Below leading one, above leading one, all entries should be 0. So below leading one, already 0. Above leading one, it should be 0. So what is the method? R2 multiplied by minus 1 adding into the first row. R1 to minus 1, that means second row multiplied by minus 1. Why we use second row? Because second row leading one present in the second row. That's why this, you can use this leading one to become here 0. So this operation. And last, here we write another 2 operation in the same matrix, but you try in the next 2 or 3 steps. And then you get the third row. Third row, first non-zero element is leading one, this is 1, and above this, these 2 should be 0. Here we use R13 minus 2 and R23 minus 1, and you can check. This is homework. You can check. These 2 are 0 and this is your matrix. And you lastly you call, after getting this is identity, the remaining matrix, this should be the inverse of this. And you can check A into B, it should be I3. You can check and verify. Okay. And these are here we provide the practice set for you. You can practice these problems. These are the some questions. Thank you. These are the reference. You can follow these books.